That is the speed for minimum power required. For a propeller-driven airplane, that is the speed that if you want to stay up the longest, best endurance, that's the speed you would fly. If you want best range, you draw a line from the origin tangent to the curve, and notice that's quite a bit difference in speed that you fly for best endurance and best range. Now, there was a fellow who set a bunch of world distance records. His name escapes me in a moment. It'll get through all the brain cells back there in a minute. But he set in a Piper Comanche. He flew from Seattle, Washington to Madrid, Spain, nonstop. Now that's a long way. That's something in excess of 6,000 miles. The interesting thing about that was he understood all these relationships real well. He understood that a reciprocating engine gets its best endurance at low altitude. Going to altitude doesn't buy you anything on a propeller-driven airplane, at least a reciprocating engine propeller-driven airplane. It's best to stay at sea level. And during his crossing of the Atlantic, I'm told he was blowing up salt spray with a propeller. That he was just above the wave tops. Set a whole bunch of world records, but he really flew around the world pole to pole. Several things like that. But he understood this curve, and he was flying at best range speed when he was doing that. Now, Piper single-engine Comanche really isn't a very big airplane. Sure, he had tanks where normally there might be people, fuel tanks, but still yet, just the volume of that airplane to be able to fly 6,000 miles with it is, pretty spectacular. Well, L over D max occurs at a higher airspeed. L over D max on this curve occurs up here where this is tangent. Remember, for the jet, it occurred down here in the bottom of the curve. Going the wrong way, I'm sorry. Well, how do the variables affect these? If we maintain a constant CL, then the weight changes, the airspeed has to change also. And here's a relation. If we start out at a weight and we get a corresponding speed, when we burn fuel off and we get to weight 2, the new speed will come through that relationship, square root of the weight ratio. And this applies in a whole bunch. You're going to be using essentially this same equation when you reduce the stalling speed data that we'll get next week. Well, air density shows its most profound differences between power required and thrust required curves. And a decrease in density caused the power required curve. Remember the thrust required curve just shifted to the right with true airspeed. Just shifted to the right at the same, stayed the same, the bottom of the curve stayed the same. Well, here's what happens with a power required curve. The power required curve, you know, this is again that best range, but notice that as the density decreases, the power increases. The power required increases to keep the same best range speed. So the best range speed in true airspeed tends to increase with altitude. So there is no advantage in a propeller-driven airplane, at least with a reciprocating engine, some advantage in a turbine. But in a propeller-driven airplane with a reciprocating engine, you're better off down here. And that was why this fellow flew blowing spray up with his propeller as he crossed the Atlantic. He stayed down low the whole flight. Now, it turned into a long flight because on most propeller-driven airplanes, this best range speed isn't real fast. In fact, on the Cherokee 6, it's probably 106 miles an hour, something like that. Flying 106 miles an hour takes you a long time to get 6,000 miles. Okay. Well, so L over D max on the power required curve moves up to the right along a straight line. And if we try to cancel that effect by plotting thrust horsepower against equivalent airspeed or calibrated airspeed, we find that we've canceled the shift to the right, but the curve still moves up. And that difference can be understood if we just look at the true airspeed. Here's equivalent airspeed. True airspeed's equivalent airspeed divided by the square root of the density ratio sigma. And here is the thrust horsepower required curve in equivalent airspeed. Notice it's picked up sigma, or square root of sigma, here to do this. And so what has happened between a jet and a propeller-driven airplane, all of a sudden, we're flying in the same air, but they don't respond to things in the same way because of what's going on in these equations. So a jet airplane, due to the fact that, if you remember, that curve slid to the right as you air density got, so a jet airplane prefers high altitude. So that's why if you get on an airliner, they go up to at least 36,000 feet if they can, or a little higher. But you get my Beech Traveler, and I'll go farther down low. I will if I go up hot. Now, I won't get a smooth ride down there, particularly on a day like today, you know, I'm getting kicked around, so, and it's hot. So, you know, generally I'll go up to some altitude where it's cooler and smoother, but I'll burn more gas in the process, okay? My efficiency for the flight will not be as good. Where on a jet airplane, it's most efficient up at the tropopause and slightly above. And that's due to two things. One, which we saw here, and the other is the fact that a jet engine prefers cool temperatures. That's why on a turboprop airplane, even though the airframe and the propeller prefers low altitude, the engine prefers high altitude, and so on the best range on a turboprop is probably someplace on the order of 12,000, 14,000 feet. From the flight test standpoint, that means that a turboprop involves more flight tests to determine where best range occurs You know, on my beach travel area, I know where it occurs. It occurs at sea level. You know, I don't have to worry about that. And I also know that if it was a jet, it would occur up around the tropopause. But on a turboprop, I'm going to have to test at several different altitudes and determine where is the best altitude, due to the fact that the airframe and propeller likes low altitude and the engine likes high altitude. Well, we've eliminated the density term here as a variable from the equation by previous manipulation of doing equivalent airspeed. But we added the density ratio term, and a density effect remains in the power required curve. So that's why that thing slides up and to the right rather than just horizontal. Well, we've already talked about this a bit. The airplane as approaches Mach 1, the parasite drag coefficient becomes a variable, varies with Mach number. Below about 0.5 Mach, that term is pretty constant. If we get above 0.5 Mach, that thing starts to increase, and that's what causes this drag rise. And so we end up with this transonic drag rise, or transonic thrust pinch, as it's sometimes called. Well, how about the available part of this? Thrust or thrust horsepower available is a function of installed thrust or thrust horsepower of the engine. Both thrust and thrust horsepower vary with air density, so there'll be a different value of power available for each set of altitude and temperature conditions. And we talked about, last time we met, we talked about on our power chart that we did a sea level side, and then we moved over to the altitude side, and turned out that the power was higher as long as we could hold a constant power setting at altitude than it was at sea level, as long as we weren't full throttle. And the reason for that was that the exhaust back pressure was lower at the lower density than it was at sea level, just due to pressure. Well, and maximum speed's a function of thrust, or thrust horsepower available, and it'll vary with those variables. So propeller-driven airplane, propeller efficiency is an additional variable, and it was, of course, going to affect what the thrust horsepower is too. Generally, propellers are designed with the maximum efficiency and the cruising speed range, and on either side of that range, they tend to drop off in efficiency. And what's going on there is that at high speeds, remember that propeller, not only does it have the speed of the forward flight coming in, but it's got its own rotational speed, and that combination is higher. So what's going on, the reason on the high end the efficiency drops off, is that we're starting to get shock waves standing on the end of the propeller. That also makes the air propeller noise go way up. On the low speed side, it's due to the blades are operating at too high an angle of attack. And generally, we can see how here's the brake horsepower available. And then in here is the propeller efficiency, and we see what happens with it. Particularly here on the low speed end, it's primarily operating at a very high angle of attack. On the high speed end, doesn't drop off quite as much, but if we went on out there, it probably would due to the fact that you're seeing a shock wave standing on the propeller tips. Okay, questions? Are you thoroughly confused? Most folks have a problem with this because hardly do we teach propeller-driven airplanes in universities anymore. Most everybody has dealt with thrust required, right? Performance classes, they talk about thrust required. Not many people talk about thrust horsepower. But when you do, you got a different set of equations to deal with. And so propeller-driven airplanes don't work the same way jet airplanes do, particularly with, you know, altitudes where they're most efficient and all that sort of thing. And like I say, today, you know, academia has rushed to the jet engine and forgot about propellers. So we're going to learn a little bit about propellers here in this class, okay? How they work. All right, I'm done. Stick a fork in me, as I say. I'm done.